Welcome back, and this is the second in the series of packs looking at the equilibrium constants. In the last pack we looked at Kc, that used concentrations to calculate our equilibrium constant. In this pack we're going to be looking at Kp, that is using partial pressures to calculate the equilibrium constant. So you're going to need your notes and a calculator. So we're talking about gases. Now the first thing we need to be able to calculate is the partial pressure of a given gas in a mixture. So in a mixture of gases, it's the pressure that the gas would exert if it was alone in that container at that particular temperature. So if you've only got one gas, then the partial pressure of that gas is equal to the total volume. So if you've only got one gas, the partial pressure of that gas is equal to the total pressure. So the individual sum of the partial pressures must add up to the total pressure. So the mole fraction of a gas is the number of moles of A divided by the total number of moles of gas. Notice it only deals with gases, not with liquids or solids. So we write the expressions in exactly the same way that we did with Kc, except we're using pressure rather than concentration. Notice we have not got any square brackets. Square brackets means concentration, so you need to be careful that you're not including them. So here we have the partial pressure of the hydrogen iodide squared divided by the partial pressure of the hydrogen times the partial pressure of the iodine gas. And as you should see here, these units will cancel out, so it will have no units. So in our second case, measuring things in atmospheres, we have ATM squared on the top divided by ATM cubed times ATM. So we've got the partial pressure of the ammonia squared divided by the partial pressure of the hydrogen raised to the power 3 times the partial pressure of the nitrogen. So that simplifies to ATM to the minus 2. So that's my units for this one. For this example, it's just the reverse of example 1. So it's the partial pressure of the hydrogen times the iodine divided by the hydrogen iodide pressure squared. Do be careful, you need to look at the equation and use the equation to calculate your Kp value. So you should see here the expression is just the inverse of the example 1, but again it has no units because they cancel. Example 4 is one which catches a lot of students out because they forget that solids are not included in a Kp expression. So Kp at this point is just equal to the partial pressure of the carbon dioxide because that's the only gas present. And because it is the only gas present, Kp is equal to the total pressure of the system. So looking at this first example, we have 2 sulfur dioxides reacting with 1 oxygen to make 2 sulfur trioxides. So again, we're going to write our Kp expression. So it is the partial pressure, and we're just going to use that kind of slanted P to stand for partial pressure, of the SO3, and that's all going to be squared, because remember there are 2 of them, divided by the partial pressure of the oxygen times the partial pressure of the SO2, again all squared. So you can put the square outside the bracket or you can put the square there, doesn't really matter. Then we need to think about units, and if this is measured in atmospheres, it becomes atmospheres squared divided by atmospheres times atmospheres squared, so that cancels and we get left with ATM to the minus 1. And there we've done the rest of them on that page for you. So again, here we've got the partial pressure of the PCl3 times the partial pressure of the chlorine divided by the partial pressure of the PCl5, so that all cancels to ATM. Now if you look at D and E, you should see that they are the reciprocal of each other. because this is nitrogen and oxygen reacting to form nitrogen oxide, and here the nitrogen oxide is breaking up to form nitrogen and oxygen gases. And so you can see here the relationship, they are the inverse relationship between these two. So it's very important that you give a balanced equation so that we know which Kp value we're actually calculating, because obviously the Kp value will change dependent on the equation that we're actually using. So we're on page 4 of your notes, and we're just looking at this typical example where we have an equilibrium mixture of ammonia, hydrogen and nitrogen, and we get asked to calculate the value for Kp. So the first thing we need to do is obviously write out our equation, because our Kp expression will be based on that equation. So I have nitrogen gas and I have hydrogen gas, and it's reacting reversibly to form ammonia, NH3 gas. In order to balance it, I'm going to put a 2 in front of the ammonia and a 3 in front of the hydrogen. I can then use that to work out my Kp expression. So that's the partial pressure of the ammonia squared, because there's 2, divided by the partial pressure of the nitrogen times the cube of the partial pressure of the hydrogen. And again, I can work out units. Well, I've got atmospheres squared on the top times atmospheres raised to the power 4 on the bottom, so it becomes ATM to the minus 2. So we've been given the moles at equilibrium, so there's no need to do the first part of the ICE table. We're just going to put in the number of moles. So nitrogen, I've got 13.5 moles, hydrogen 3.6 moles, and I've got 1 mole of ammonia. Now, to work out the partial pressure, I first need to work out the mole fraction. So that's the moles that I have divided by the total number of moles. Well, the total number of moles, if I add all these up, it equals 18.1 moles. So the mole fraction is my fraction, 13.5 divided by 18.1, 3.6, and 1 over 18.1. And I've worked those out. Now, what I need to find out is the partial pressure. So I need to times my mole fraction by my total pressure to find the partial pressure of each component. So rather than putting this number in my calculator, I'm going to keep this number. I'm going to put this number back in my calculator, and I'm going to times it by the total pressure, which is 2. So I've got 13.5 over 18.1 times by 2, and that will give me my partial pressure, which is 1.4917. Try not to round too much until you get to the end point. So we're going to keep a large number of significant figures here, so we don't introduce rounding errors. And I've worked out the hydrogen and the ammonia in the same way. And lastly, what I need to do is to put these values into my expression for Kp and to solve it as normal. So I have the partial pressure of the ammonia, and I've got to remember that that is squared divided by the partial pressure of the hydrogen raised to the power 3 and the partial pressure of the nitrogen raised to the power 1. So I've got 1.4917 times 0.39779 cubed, and that all equals 0.130 to 3 sig figs, and the units are ATM to the minus 2. So that finishes this video just looking at an introduction to Kp. What I'd like you to have a go at doing now is the examples on the next 3 pages. And we'll go over those in the next video. So until then, take care, stay safe. Bye-bye.